topic called equal area criteria. So this is again very important topic in the area of power system analysis. So before we get on with today's class, let's first review what we have done in the previous lecture. So I'm just opening the lecture notes of the last lecture. Okay, so this is what we had done just on Tuesday. I started the topic of power system stability, but for understanding power system stability, it is important to have a review of synchronous machines first. So what I've done is this is the three-phase supply: line A, line B, and line C. And the stator of a synchronous machine with a three-phase winding is connected to the three-phase main supply. And the frequency of the supply is F. So you know that if I connect the stator to a three-phase supply with frequency F and the number of poles is P, then the synchronous speed Ns is given by 120 F by P. This is a very, very well-known expression for power. So three-phase supply results in rotating magnetic field in the air gap. So the rotating magnetic field right now, it is downwards. It can be this way, it can be this way, and so on. It is continuously rotating at the speed of synchronous speed. So as a resultant, the stator can be represented as a two imaginary magnetic poles. There's a one north pole here, one south pole here, and this north pole is rotating at a speed of synchronous speed, and this south pole also rotating. So these two together are rotating around the stator. So they are not actually physical north pole and south pole. These are the poles which are generated out of the rotating magnetic field in the stator. So this is north pole and south pole. This is a magnetic field. That is about stator. Now coming to the rotor, what we have in the rotor is an electromagnet with a DC current flowing in the electromagnet. As a result, there is a north pole and south pole in the rotor also. Now, on the other hand, for the rotor, I can also connect the mechanical load. This mechanical load will try to decelerate the rotor. So there is some kind of magnetic locking happening here. So the north pole and south pole of the stator will lock to south pole and north pole of the rotor. There's a magnetic locking between these two. Therefore, if this stator pole is moving at synchronous speed, the rotor pole also moves at synchronous speed. Ns equal to Nr, and there is no relative speed between them, and then these two are magnetically locked, and that is the definition of synchronous machine. Why it is called synchronous machine is the both stator and rotor both rotate at synchronous speed. Either the rotor will rotate at synchronous speed or the rotor will stop. So that means either it is in magnetic locking or it will simply stop working as a motor. So that is why it is called synchronous motor, and magnetic locking is very, very important. Now we discussed what is the effect of loading the rotor. So if I load the rotor, then there is a load torque applied on the shaft that will momentarily slow down the rotor. So when the momentarily rotor is slowed down, you see it in the next figure, the rotor is rotating backwards, or relatively rotor is going back by delta M. So this delta M is the angle which is the effect of the load. Now as a result, you see there is a still magnetic locking going on there. The magnetic locking is still there, and the amount of force that is generated here, electrical force, will be proportional to the amount of loading, such that finally the delta M settles at some stationary value, and there is now more locking between, more magnetic force between these two, so that they can counteract the load. So the load is torque is Tm, and the electrical torque generated is Te. So these two cancel out each other. Now the stator is rotating at synchronous speed, the rotor also rotating at synchronous speed. The synchronism is maintained, it is still magnetic locking is maintained and so on. Now coming to synchronous generator, we have grid connected and off grid. We are only discussing grid connected as a moment. So therefore, since it is grid connected, just the stator is connected to the grid and rotating magnetic field is set up. This is exactly same as what we discussed. But coming to the rotor, it is slightly different now. Here, instead of a load connecting to the shaft of the rotor, I am connecting a generator. So I am actually providing mechanical energy to the rotor. So in that case, momentarily, the rotor will accelerate more than the stator and then this rotor will move forward. So that is what is shown in this diagram. The delta M is now positive. So in the earlier case, delta M was negative. So when the rotor moves forward, the stator tries to pull it back and still the magnetic locking is maintained and therefore synchronism is maintained, NR equal to NS, and then it is still running as a synchronous motor. So now the issue is, if I gradually add the power, then gradually it will increase and there is a scope for this magnetic locking to be maintained. But if I have a sudden increase in the load, the magnetic locking will be lost and therefore the motor will come out of stability. So that is the stability problem. Okay, let's continue. This is to summarize. The synchronous motor is like this. This is the shaft and this is the rotor. So electrical power is entering into the motor from the right side and the mechanical power is leaving from the left side. So in between, the electrical power is generating electrical torque Te and the mechanical torque is Tm and then the speed of rotation is in this direction. So in a synchronous motor, the speed of rotation and the speed of electrical torque both will be in the same direction. Now under steady state conditions, P equal to Pm. So net energy entering into the or net power entering into the rotor will be equal to the net power leaving the rotor, not considering losses. So therefore, the omega m will be maintained constant. So whereas in the synchronous generator, the Pm is entering from the left side and electrical power is leaving from the right side. And then now this time the twisting motion, the torque is in this direction and the rotation is also in this direction. So compared to the previous one, the rotation has been reversed. So the previous one rotation is like this, whereas here the rotation is like this. So again the same condition applies. Under stability, Pm equal to Pe, Tm equal to Te. So ultimately what we are having is mechanical power stored as kinetic energy and released as electrical energy in the case of generator. So if there are any disturbances on Pe or Pm, how the kinetic energy is managed and how the system is having stability is what is the problem. So for example, in this there is a fault. So when there is a fault, the switch S is closed and the zero voltage applied to V1. So therefore electrical power completely becomes zero, but mechanical power is still there. So the rotor will accelerate. But then later on when the fault is cleared, the rotor should decelerate and then settle to its original value. So but then how much time is needed for the fault to clear? It is called critical clearing time. We are going to see this today. So that is the stability. So then we moved on to derive the swing equation. So what is swing equation? So swing equation is nothing but equation which represents the variations in delta. So you know famous equation F equal to ma. This is for linear motion. For circular motion, torque equal to J into alpha. Alpha is the angular acceleration, J is the moment of inertia and T is the torque on the rotating object. So in our case, the net torque is mechanical torque minus electrical torque, which is equal to J, and then acceleration can be represented as a second derivative of the position. Time is the position, so second derivative is the acceleration. So here I am doing a simple change of variables. I am taking theta m is nothing but omega sm t plus delta m. So this is a rotating reference frame. With reference to that, I am measuring the changes, this one. So first derivative is this, second derivative is this. So I can directly replace it with delta m. So the equation becomes this. So here I multiply with omega m on both sides. Then I get in terms of power. So Pm minus Pe is the mechanical power minus electrical power. This is called accelerating power. If the accelerating power is positive, then the delta M will be accelerating and the delta M will increase. Whereas this Pm minus P is negative, then delta M will decrease. So here simple substitution j omega M I substituted with M. M is called inertia constant. Then we also looked at the kinetic energy of rotating object, and then in terms of that I am defining M. And another constant is H, stored kinetic energy in rotor by this. So again I have this. So by just simple manipulations, finally I got this equation, that is 2h by omega m equal to this one, and S rated will become this one, and finally it will be in per unit. Now this is swing equation of a machine in with mechanical load angle. So that is why delta M and omega M is there. Now I want to express this in the electrical load angle. So just simply substitute this by pair of poles. So electrical angle is nothing but P by 2 into mechanical angle. Similarly, electrical radiance omega is nothing but P by 2 into omega. So if I substitute these two, the two P by 2s will cancel each other, and finally I get this equation. That is 2h by omega into second derivative of electrical delta is Pm minus P per unit. So this is where we stopped the derivation yesterday. So this is the final swing equation. So we are going to refer to this equation today. We are going to work on this swing equation. So let's move forward. So we did a small problem considering some data and all. So a 50 Hertz 100 MVA 4-pole synchronous generator has an inertia constant of 3.5 seconds, and then the base MVA is given, and then the per unit powers are given. The problem is the mechanical power is slightly increased from 0.16, which is a stable value, to 0.18. So slightly increasing of mechanical power. So what happens to the rotor? Of course, the rotor will accelerate. So we have to find energy stored in the rotor and then acceleration of the rotor. So energy stored in the rotor is straightforward because H is given and machine rating is given. So from that I can find the energy rating. So 350 megajoules. Next I find the accelerating power, that is 10 megawatts. So at 350 megajoules, if I supply 10 megawatt, how much it will accelerate? So again, simple calculations we have done. And from that we find that the acceleration is 257 degrees per second square. So this is degrees per second square is the unit of angular acceleration. So meters per second square is the unit of linear acceleration, whereas the angular acceleration is this one. So okay, so let's continue with today's class. This is what we have done until the last class. Mainly what we studied is the swing equation of the motor or a generator, which describes how the delta varies with respect to variations in the PM and PE. So any doubts up to here based on what we discussed, you can ask. This is the main swing equation what we derived last class. So if you have any doubts, please feel free to ask. I'll wait for a couple of minutes. Then we'll start another topic that is the continuation of this equal area criteria. So any doubts on this? On an equal area criteria. But before we go to that equal area criteria, let's we begin our study by deriving that electrical power generated. So imagine that there is a generator and then it is connected. Now this is the terminal of the generator. This is the internal bus of the generator. So internal EMF generated is EG and at an angle of delta. This is the X reactance of the machine. So I'll put JX, and this is the infinite bus. So it is it's a voltage. So the voltage is 1.0 angle, or let me just represent V angle 0 degrees. So now I want to find out what is the expression for active power generated from the generator. So if I maintain the angle of delta, and if I maintain here the infinite bus angle is taken as reference 0 degrees, how much power is generated through this machine. So it is very easy to derive that. So first derive what is the current. So what is the current I? So current I is nothing but potential difference, that is Eg delta minus V angle 0 degrees divided by the impedance Jx. So this will be my current. Now I can actually further simplify this. So I will be equal to, so Eg by x delta minus 90 degrees, sorry this is capital X, minus V by x, here angle will be minus 90 degrees. So this is my current. So now once I know the current, I want to find out the complex power, or actually I want to find out the active power, but let's first find out the complex power. How do you find the complex power that is reaching this particular terminal V? So the complex power is V into I conjugate. So complex power is nothing but V into I conjugate. This is complex power received by the terminal. So this is the infinite bus. So how much it is receiving? So that is this. So now V anyway angle is 0. So I can consider it as a constant and multiply it. And I have to take conjugate. So I conjugate means this, the angle sign will become reversed. So I'll get Eg by into V by X. And here the angle will become reverse, 90 minus delta, because I conjugate have to take. So minus V square by X, and here also angle minus 90 will become plus 90 degrees. So this is my complex power. Now complex power, see complex power is nothing but P plus JQ. So right now I am not interested in Q, I am interested only in the P part of it. So P part, it's nothing but cos of the angle. So S is nothing but, complex power, active power P is nothing but, you take Eg into V by X. And then here I will take the cos component of it, cos 90 minus delta. And then here, so minus V square by X cos of 90 degrees. So this term will be equal to 0. And this term I'll get active power generated is nothing but Eg into V by X sine delta. Now if this is electrical power output of the machine. Now if I define this quantity, so Eg is fixed, I am assuming that the voltage magnitude is fixed. Similarly V is fixed, and similarly X is also fixed. So this is a constant. Let's denote this as P max. Then I'll get the electrical power is nothing but P max multiplied by sine of delta. So this is the expression for electrical power. Now if I draw it in the form of a graph, so this is my axis. So on x-axis I'll mark delta, on y-axis I'll mark the electrical power. So then I'll get a line which is like this, because it is a sine curve. So this is nothing but electrical power generated. Now this value is called P max. So P max is a known constant. Why it is known? Because I know how much voltage I am generating and what is the terminal voltage I know. So based on that, and X also we know, so based on that it will be there. And this P max power occurs at an angle of pi by 2, 90 degrees or pi by 2. This is pi degrees and this is 0 radians, and this is 0 radian, and this is the value of delta. Power, electrical power generated. So any doubts about this? What I have done is very basic. Then first I calculate the current, then the current I can write like this, then the conjugate of the current, then multiply it with the receiving end voltage, and then only you are worried about the real component, so cos component, then finally we get like this, cos 90 minus theta is sin theta. So we are getting like this. So this is let. Three max, and then finally I'm getting the power angle, sorry, the power relation like this. So this is very important. If you have any doubts, feel free to ask right now. Intuition of it. So I'll just delete this line. So imagine that there is a north pole here and there is a south pole here. As I was explaining, this is the stator. So this is rotating at synchronous speed. Now the rotor, if you consider this as a generator, then the rotor will be accelerating. So this is my axis. So from this, so this is south pole and north pole of the rotor, and then this angle, whatever comes between these two, is on the x-axis of this glass. So when the angle is zero, the power, electrical power is zero. That means when completely aligned. So if it is like this, north, south, north, and south. So if everything is like this, delta equal to zero, so electrical power equal to zero. So the maximum power that comes is when it is completely 90 degrees like this. So this is south pole, this is north pole. So because this attraction in magnetic locking is there, so this is the maximum. So P max, delta is pi by 2. So this is the angle delta. Delta is pi by 2. So in between, it varies like this. And now if I further increase, you see the power is reducing because the sine curve. So that is also intuitively you can see from this diagram. So first, I hope you understood this diagram now. Next, now you come to the concept of operating point. So what is the operating point is, so you have a machine. So this is a machine. This is actually synchronous generator. So input is mechanical power PM, output is electrical power PE. So the output is like this. This is PE. And the P max is defined here. So question is now, can I generate more than P max? So it is not possible to generate more power than P max because of the reactance of the machine. So what is P max? P max is nothing but Eg into V by X. So to generate the maximum power limit actually is limited by X. If the X is more, then the P max will be less. So it is preferable to have low reactance for your generator. Similarly, I can increase, if I want to generate more power, I should go for higher voltages, Eg and V. That is about Pmax. I cannot generate more than Pmax. But I should not generate completely Pmax. I should generate something less for the stability reason. So I already indicated this is pi by 2. Anyway, so now let's draw one horizontal line like this. Let's say this is PM. This is the mechanical power input to the motor. Input to generator. So who determines the PM? So PM is determined by the user only, because by the input power, input steam input can be controlled. By controlling the valve, I can generate more steam and I can send more steam into the machine if it is a thermal generator. So by controlling the prime mover, I can control the PM input. So PM equal to PE under steady state condition. So we have 2 points, either here or here. So let's consider this as my delta naught. So delta naught is the operating point. While this one is not an operating point because this is unstable. Why it is unstable? If there is any slight increase in the electrical power, then it will keep on, the mechanical power is still less, so it will keep on decelerating and it will not come back to the normal plane. But whereas here you see, whenever there is a slight increase in the electrical power, delta will increase and then there will be a compensation and then it will be under stability. So this point is stable, this point is unstable. Or to consider it such another case, let's say slightly I move right side. So I am moving it, for example. Due to power is more, mechanical power is less. So therefore, the more energy is removed from the machine, therefore machine will slow down and come back to delta naught. So if I move right, I'll come back to left. Similarly, if I move left, then the electrical, that means if I move left, that means the machine is slowing down. If the machine is slowing down, the mechanical power is more than electrical power. Therefore, again, machine will speed up. So any disturbance, small disturbance, it will be like this. So this point is actually like this, delta naught. If there is a rock here, if I move right side, it will come back normal. If I move left side also, it will come back to normal. So this is the delta naught operating point. So normally the generator is operated. So this is this delta naught. So we have 0 to 90 degrees here, or pi by 2. So if you are operating at 0 degrees, of course you are not generating any power. But if you are operating at pi by 2, you are very close to stability limit. So you don't, this is a dangerous area. So typically you operate. So typically your delta naught will be less than 30 degrees. So this is the typical operating point of a generator. So any doubts up to here? So I'm just pausing to check if anybody has the operating point. So what happens if I move away from the operating point is what we want to study. So I'll just physically explain here. So consider step increase in input power mechanical PM. So I have a system like this. And then right now, this is my electrical power and this is my mechanical power. So this is PM1 and PM2. So suddenly there is a step increase in the mechanical power input to the motor. So I'll just draw the motor also. So just for you to understand, this is synchronous generator. Electrical power is leaving the machine and mechanical power is entering the machine, and there is some kinetic energy stored in the machine. Now there is a step increase in the PM. So before the step increase, this was my normal operating point. So let's call this as delta naught. This is my normal operating point. Now what happens if I suddenly increase the input power? Then so from this point I jump to this point. So I'm electrical power I am still generating less, mechanical power I am generating more. So therefore mechanical power is more than the electrical power, and therefore it will accelerate. Just a minute, I got a call, so I'll just, so delta 1. So this gap which is there, so this is delta 0 and this is delta 1. So delta 1 will be greater than the delta 0 because that is corresponding to the new power input. So that is the phenomenon that is happening. So as a result, these two areas are created. So these two areas will be equal, and that is why it is called equal area criteria. Now the question is, here I am only considering a very small variation in the power. What if it is very large variation? So if there is a very large variation, then there will be a problem of stability. So I'll explain that with or otherwise let's derive the condition. Okay. So whether the machine will be stable or not. Okay, or maybe I have some, I'll just quickly explain here with a large input, large disturbance, large step input to the generator, synchronous generator. So now what happens? So let's take this axis. This is the electrical power generated by the machine. Let's say I'm operating here. And this angle is delta 1. So this is P1, PM1, mechanical input 1. Now suddenly I increase to somewhere this value. So here what happens, this is PM2. So this increase is very drastic. So this operating point which can start here may overshoot this point. So let's call this point as, let's say, delta max or delta critical. So if I exceed this point, then again it is difficult for me to come back because I'm not able to get back to the synchronism. So because this is supposed to be my final point, but if I overshoot, then I completely move forward and then I'll not be able to come back. So this condition should not happen. So here what happens is, let's call this as area A1. Let's call this as area A2. So if A1 is greater than A2, then stability is lost. So this is what we have to see today. Okay, so let's continue. I'll go to a new page. Whatever is the supply frequency, then I have PM is per unit mechanical input and PE is per unit electrical output. So what is the condition under steady state condition? PM minus PE should be equal to 0 because the acceleration should be 0. So acceleration is 0 means your velocity is constant. Angular acceleration should be equal to 0 for constant velocity. So I want the machine to operate at a constant speed. For that, the acceleration should be 0. So that is the condition. So but anyway, so it will not be 0 because whenever there is a disturbance between PM and PE, it will become non-zero and again it should become 0. Okay, so now from this, I want to find out what is delta. So this is a differential equation, I want to solve it. So we use one small mathematical trick to solve it. So what I'll do is I have 2h d square delta by dt square 2h by omega equal to Pm minus Pe. So first let me write like this: d square delta by dt square equal to omega by 2h multiplied by Pm minus Pe. So I've just brought this term to the right hand side. Now what I will do is multiply on both sides with this term, that is 2 d delta by dt multiplied here, and here also I'll multiply 2 d delta by dt. So I'm multiplying with the term on both sides. Why I'm multiplying with both sides is just look at this. I'm just going see what is so this, let's call this as equation 1. Just for this, what is the integration of 2x dx? The integration of 2x dx is x square. Why? Because this integration of x is x square by 2, and 2 will cancel. So it is like this. Now look at this. This is exactly same as this. So in the place of x, I have d delta by dt. In the place of dx, I'll have derivation of d delta by dt. So these two are very similar. So from by integrating left hand side, I'll actually get x square, that is d delta by dt whole square. So this I'll say since. So we get by integrating integration of equation 1. So if I integrate this equation 1, this will become d delta by dt whole square. Just a minute. Integration of 2x dx is so on the right hand side, here I'll get something like this. So I have to apply integration to this. So I'll get omega by 2h. These anyway, I'm writing this because these are constants. Omega is constant, h is constant, whereas Pm, Pe are a function of delta. So in fact, this 2 also can be brought out. So 2 will cancel each other. So let me just write omega by h. Integration of Pm minus Pe with respect to d delta, and delta varies from some delta naught to some delta. So finally, this is what I am getting on integrating both sides. So from this, I get d delta by dt is equal to square root of this term. So what is d delta by dt? This is nothing but angular velocity of the rotor, or in common language, this is nothing but speed of the rotor. So this is speed of the rotor with respect to synchronous speed. So now speed of the rotor with respect to synchronous speed should be maintained 0. So for stability, d delta by dt should be equal to 0. So therefore, this term is nothing but 0. This whole term is 0. So therefore, square root of omega by h integration delta naught to delta Pm minus Pe d delta should be equal to 0. Or in other words, Pm minus Pe d delta should be equal to 0. So this is the condition for stability. Now, what is integration of anything? Integration is nothing but area under the curve. So if I just look at this, so this is Pm, this is Pe. So what is Pm minus Pe? So Pm minus P. So this in the initial part, Pm is more and P is less. So this is Pm minus P, which is positive. And then integration. So let's consider this as delta naught and this one. So this is the area defined in the first part, and this is the area defined in the second part. So this is the another area. So let's call this as delta max. So between these two, I have area 1 and area 2, and one is the negative area, one is the positive area. These two areas should cancel out each other so that the final value is 0. Then the machine is under synchronism. Otherwise, it is not under synchronism. So that is what is the equal area criteria. So from this, we will also get the equal area criteria. So this is the equal area criteria of the machine. Any doubts up to here? Done. Looked at the swing equation of the machine. From the swing equation of the machine, I multiplied 2 d delta by dt on both sides and then integrated it. Then I got this expression. Finally, I get this condition for stability. That is Pm minus P into d delta should be 0. Any doubts on this? Application of step input increase in the P mechanical. So already we have done this topic, but then now we'll actually do some calculation also. So let me draw the diagram neatly. So I get a so this is my electrical power PE, and then I want to show my initial condition. This is PM naught and this is PM1. So I am initially operating at this point, and delta naught is my initial angle. So let's label this point as A. So let's do our discussion. So when I increase the power from PM0 to PM1, then from point A I'll move upwards. So my mechanical power is more, electrical power is less. So machine will accelerate, and then this point A will move towards the right side. But it will overshoot, and then it will go up to a point. Let's call this point as D. this point is A. In between it will go through point B and then this point is C. So at this point, electrical power is more, mechanical power is less. So again, the motor will, the generator will start decelerating. Again, it will come back. So finally, it will go and then settle at point B. So let's mark this point as delta max. The maximum value attained by delta, and then let's mark this point as delta 1. So delta naught is the initial operating point, delta 1 is the final operating point, and delta max is the maximum value that is achieved by the delta. Okay, so now what is the condition for stability? Just now we derived. What is the condition for stability? Integration from delta naught to delta, whatever is the final value of delta, it should, of the quantity Pm minus Pe, should, with respect to d delta, should be equal to 0. So this is the condition for stability. Now, what is Pm? So in our case, right away Pm, at the beginning itself I am considering step input 1. So I will put Pm1 here. So now what is Pe? Pe is the electrical power. Just now we derived, that is P max sine delta. So this is Pe, this is the electrical power derived. So if I now substitute that, I'll get an expression something like this. Condition for stability. That is delta naught to delta integration Pm1 minus P max sine delta d delta should be equal to 0. Now, if I go up, what does this indicate? This, I'm interested in area, this area and this area. So I'll split the integral into two parts. I'll split the integral from delta naught to delta 1. I'll split it. So, but our original this thing, so these two areas should be 0, or subtraction of these two should be 0. So what I'll write is something like this. Delta naught to delta 1, same thing, Pm1 minus P max sine delta. So this one anyway I know will be negative because Pm is more and sorry, this area will be positive. So plus delta 1 to delta max, Pm1 minus P max sine delta. So with respect to d delta, with respect to d delta should be equal to 0. So this is my condition. So let's actually do the integration. So when you integrate, what is the integration of this term? So this is Pm1 into delta. What is the integration of this term? Integration of sine is cos. But then the integration of sine is minus cos. So this minus sign will go. So it will become plus P max cos delta. This is delta naught to delta 1. Here I'll get Pm1 into delta 1 to delta max. And then this will again become plus P max cos delta. Again the limits will be delta 1 to delta max. This all should be equal to 0. Here I can substitute. So Pm1. So here I'll get delta 1 minus delta naught. Here I will get delta max minus delta 1. So I have taken care of this term and this term. Next, the other two terms. So I'll get plus P max. So here cos of delta 1 minus cos of delta naught. Here I'll get cos of delta max minus cos of delta 1 should be equal to 0. So some terms will get cancelled. These two terms will cancel, and then these two terms will get cancelled. So finally I am getting Pm1 into delta max minus delta naught plus P max into cos of delta max minus cos of delta naught should be equal to 0. So I am getting finally some expression like this. Now if I go to the diagram, now look at this Pm1. So Pm1 I can actually express in terms of delta. So Pm1 is nothing but at this point whatever is the this one P max of sine delta 1. So let's go forward. So I'll just take to the other side. So the sign will reverse, cos of delta naught minus cos of delta max. So Pm1 is nothing but P max of sine delta max. So this one, if I just substitute it here, so I'll get sine of delta max multiplied by delta max minus delta naught will be equal to cos of delta naught minus cos of delta max. So if you notice this particular expression, this is I'll once again rewrite it. Delta max minus delta naught into sine of delta max equal to, plus cos of delta max minus cos of delta naught equal to 0. So this is the expression. This is condition for stability. So in this is known. Delta naught you already know because that is coming from the initial conditions of the machine. This is also known. So only unknown quantity in this is the unknown. So we have one equation and one unknown, and we have to find that unknown. And by finding that unknown, we are able to find what is the maximum value of delta that will keep me under stability. Otherwise, I lose my stability. So this is the thing. And we also know, like if a particular equation is given and delta naught is given, how to find the delta max. Because this is a nonlinear equation, you will have to solve it iteratively. But I have a easy method to solve this. In fact, we'll be trying to do that. So this is actually, you notice that Pmax also got cancelled. So this is completely a geometrical problem. So what is the geometrical problem? I'm just looking at this diagram. If this is known, find out the delta max for which the stability is maintained. So if I consider delta max somewhere here, then after a particular while, for a higher step input, it will not be able to handle the stability. So let me explain what I'm saying. So let's say in the above equation, if delta naught is known, then delta max can be found. Okay, so there is a doubt. Isn't PM1 is nothing but Pmax sine delta 1? So let me just check it. I'll just come back. I think there is an issue with the notation. Let me just check it and come back. Okay, so the doubt asked is PM1 equal to Pmax sine of delta 1. So actually this is correct. It is also equal to Pmax sine of delta max. So that is because I created confusion by drawing a wrong figure. So let me correct the figure. So I just go up. So there is some problem with this figure. So let me write the figure in such a way. I'll just delete this figure and redraw the figure. So the PM, I'm just redrawing the figure. This is my electrical power PE. Let's delete this also. Okay, let me do a little bit of explanation. See, this is initial value PM naught. I'll take PM1, I'll take PM2, I'll take PM3. So if I start here at delta naught, if I jump from PM to PM1, this is my area. So how much area I can get on the right side is equal amount of area, somewhere this much. So my maximum value for delta will be up to here, delta max, and it is stable. So PM naught to PM1 stable. So now if I jump from PM naught to PM2, then let me just delete this part. Now if I jump from PM0 to PM2, this is my area. So this much area I have to get from the right side. So maybe here, this area, somewhere here, if I just cut it here, so it is satisfying. So let's say this area equal to this area. So then the maximum value of delta will be like this. So delta not is known, delta max is unknown. So it is achieving up to this much. So what is the limit? So let's look at PM3. So PM0 to PM2 also stable. Now again I delete this. Let's consider PM3. So this much is my area. But if I look at the electrical, this one, this much area, so this area 2 is less than area 1. So I'm not able to, even if I go to this point, even if I completely go to this point, I'm not able to collect the positive area. So positive area is always less than this one. So PM0 to PM3 unstable. So this is like you consider, so it is stable from here, this much step it is stable, this much step is stable, but it is not unstable because area 2 is less than area 1. So what is the limiting value? To that much power I will be able to handle it. So then the diagram will become something like this. So if I'm really interested in that particular this one, so what I'll do, I'm sorry. So what I'll do is I'll choose a point. Let me just roughly check it. I will choose a point PM1 as my maximum point. So where this entire area is utilized. So this is complete area is A2, this complete area is A1. So under this condition, A1 equal to A2. So this is the extreme condition. So under this extreme condition, both areas are equal. So that is why now what we have on the x-axis will be like this. So let me delete all this. This angle is, sorry, this angle is delta max and this angle is delta 1. So from these 2 points, I can note that PM1 is nothing but sine of delta 1, but PM1 is also nothing but sine of delta max. So PM1 is nothing but sine of delta 1, which is nothing but sine of delta max. Of course, P max into. So that is why I have substituted delta max. So I hope that clears your doubt. So under extreme condition, these two areas are equal and then therefore these 2 points are same. Okay, so any doubts up to here? Just note down this whatever is here marked here. Note down this equation. We are going to solve it, and we are going to understand more about that. Example problem so that you will understand further. So the problem is like this. So I have a prime mover. So this prime mover is giving PE. So this, let's say it's a turbine. Sorry, this is giving PM. And then there is a generator. And this generator is generating the electrical power PE. So let's call this as generator. So this PE power is generated. So EG is the internal voltage of generation, delta naught is the initial angle, X is the reactance of the generator, and then V is the terminal voltage of the generator. So this is the system. Now, given data, the terminal voltage is 1.0 angle 0 degrees and the reactance is J 0.6 and the EMF induced generated by the machine is, let's say, 1.25. So I am only giving the magnitude, delta value I am not giving. So magnitude of EG is this one. So delta naught unknown. Now under steady state condition, PM naught is equal to 0.6 per unit. And so therefore P naught is also equal to 0.6 per unit. Because under steady state condition, PM naught equal to PE naught. From this I can find the delta naught. So now I want to go for step increase of PM naught. So determine maximum step input increase in PM naught allowed such that stability is maintained. So please understand the question. So that these are the parameters given to you. Now if I increase, so PM, if I give a step increase, there will be some stability problem. How much step increase I can withstand? So is it 0.6 to 0.8 or 0.6 to 1.0 or 0.6 to 1.2? How much step input is allowed for PM naught so that the machine does not lose synchronism? So this is the problem that we are trying to solve. So how do you solve? So first you go by calculating Pmax. So what is Pmax? Pmax is nothing but Eg V by X. So EMF, these are all magnitudes. So EMF generated is 1.25 and then voltage of the terminal is 1.0 and X is 0.6. So let's calculate how much it is. So I go to my Octave interface. So 1.25 by 0.6. 2.08 is my Pmax. So now, what is my actual P naught? So P naught is, so how to get the delta? So we have a situation like this. This maximum value is 2.08 per unit at 90 degrees. Now I am operating at 0.6 per unit. That is P naught equal to PM naught equal to 0.6 per unit. Now what is the delta? Delta naught. So you notice that PM naught sine PM naught equal to P max sine delta naught. So therefore delta naught will be sine inverse of P max by PM naught. So let's do that. So is sine inverse of 2.08 divided by 0.6. Oh, sorry, this is actually reversed. So this is PM naught by P max. Sine inverse of 0.6 divided by 2.08. So I'm getting 0.292. This is in radians. So 180 by pi. So I'm getting 16.76 degrees. This is delta naught. So finally I got 16.76 degrees as the delta naught. I'm operating at this point. Now my next question is how much I can go for step input such that I am still maintaining the stability. So in other words, I'll draw once again here. This is 16.76 degrees angle. So if I make these two areas equal, so A1 equal to A2, in that case, what is the delta max? This is my question. And what is delta 1 is also my question. Of course, if I solve for delta max, I'll get delta 1. Both are, I can see here, both are equal from this. So this value I already know, this is PM naught 0.6 per unit. So what is this PM1 question mark? So this also I have to find out. So here is where we use our equation to solve it. So I go back to my previous derivation. So I asked you to note down one equation. So that is what I'm bringing it here. So this is my condition for stability. So delta naught we already calculated just now, 16.76 degrees. So I want to calculate this function. So represent it as f of x or function of delta max equal to 0. So this function value I want to make it 0. And I also know that, see, this is how many radians. So if I go here, this is pi by 2 radians and this is pi radians. So pi by 2 means 3.14 by 2 or 1.57 radians. And whereas this one is 3.14 radians, that is pi radians. So the answer is between 1.5 to 3.1. So if I just take only one day, the answer is between these two values. So I want to find out what value of delta max will give me the maximum stability, will give me the stability limit. So you see what I'll do now. So just make a note of this equation, delta max minus delta naught into sine delta max plus cos delta max minus cos delta naught is equal to 0. So I want to make this value 0. Just make a note of this equation. So let me now switch to my Octave interface. So here I'm just clearing all the variables. Here I'll write a simple program. The program is like this. So what is D0? D0 I got 16.76 degrees. So 16.76 degrees I will divide by 180 and multiply by pi so that it is converted into radians. So 0.29252 radians. Okay. Now what is D max? So I know that it is a value between 1.5 and 3. We know that delta max is between 1.5 and 3.1. So I will start with 1.5. This is my initial value of Dmax. Then I'll calculate the function value. So f of Dmax. So I'll just represent it as a capital F. Dmax minus D naught into sine of Dmax plus this is into plus cos of Dmax minus cos of D naught. So this is my function. Let me scroll that. So now you are able to see that. So this is my function. Now if I run this program, so what is the function value? 0.31. The function value is positive. I want the function value to become 0. So if I increase the Dmax, then it keeps on changing. So I'll just say while f is greater than 0, I'm giving this condition. So Dmax I'll slightly increase. 1.5 I'll increase plus 0.1. Then I calculate the f value. And then I display both the Dmax and f values. Display Dmax and f. So now if I run this program, I'm sorry. I think I made a mistake. Actually, this should be Dmax plus. Otherwise, the while loop will never end. I think code is still running. I think I went into infinite while loop. So let me restart the code. Just give me a minute. I'll restart the code. Because of that, my program got hanged. So I'll just once again open the code. Okay, so now you are able to see the same. So here it should be Dmax. So while the F value is positive, I'll run this. So now if I execute this, so I'm getting this. So 1.5 was the starting value, then 1.6, 1.7, 1.8, 1.9. The value is gradually reducing. You notice? And at the last, between 2.1 and 2.2, the value is changing from positive to negative. That means my answer is between 2.1 and 2.2. So that is how I can find out. So let's go back to the code. I put 2.1 as my starting point. Then in the D step, I'll put 0.01 as my increment. Now, if I once again execute this program, so now I'm starting with 2.1, then 2.11, 2.12, 2.13. Like this, I'm gradually increasing the value of delta max. And at a point where 2.19 is changing to 2.20, the value is changing from positive to negative. That means the answer is between 2.19 and 2.20. So again, I'll come back here, I'll put 2.19 and then I'll increase one more decimal. Now once again, I'll run the code. So here you notice 1.2.191, 192, 193, 194. Between 2.196 and 197, the value is changing from positive to negative. So I'll consider 2.196 as my final value. So this is the simple code to solve this thing. So what I am writing here is now by solving we got delta max equal to 2.196 radians. So let's convert that into degrees. 2.196 into 180 by pi. So this is 125.8 degrees. So the final answer is, so if my initial angle is 16.7 degrees, then I can go up to, so this is 90, sorry, I can go up to 125.8 degrees, such that these two areas are equal. This area is equal to this area. So this 125.8 degrees is my delta max. Now from that, can I calculate what is P1? So P1 or PM1 is nothing but P max into sine of delta max. So this is 2.08 into sine of 125.8 degrees. So let's do that. 2.08 into sine of 196. So this is 1.68 per unit. That means I am operating at PM naught of 0.6 per unit. Then PM1 is 1. The machine can tolerate step input of 1.08 per unit maximum. So if I give a step input of more than 1.08 per unit, the machine will lose synchronism. So that is the stability study that we are able to do through this equal area criteria. So since the time is up, maybe last 2 minutes, any doubts you have, please feel free to ask. I think this is the last lecture as per the timetable, but then if I am actually planning to wrap up this, give one entire summary lecture, and there are some more topics in equal area criteria. So I might record one more lecture and I'll keep the notes available. Otherwise, this would be my last lecture. So it was great delivering this course online. I hope most of you have followed all my lectures. Also, my homepage is there where you can download the notes. So feel free to ask doubts anytime. And I thank you all for your participation in this course. Any doubts you have? So I also thank the JNTU for organizing this, especially Professor ASN Chakravarti. He has been very helpful. All the time he has been given his support. So if there are no doubts, then let's call it a day. Let's see if there are more courses in the next few semesters. We'll once again